Okay, we're on our last section, chapter 19.10, or section 19.10, magnetic domains. And let's get right to it. Let's think about the source of a magnetic field. We know a single coil like that in the figure has a north pole and a south pole. But if that is true for a coil of wire, it should also be true for any current confined to a circular path. In particular, an individual atom should act as a magnet because of the motion of the electrons about the nucleus. Each electron, with its charge of 1.6 times 10 to the minus 19 coulombs, circles the atom once about 10 to the 16 seconds. In about 10 to the 16 seconds. If we divide the electric charge by its time interval, we see that the orbiting electron is equivalent to a current of 1.6 times 10 to the minus 3 amps. This magnitude current produces a magnetic field on the order of 20 Tesla at the center of the circular path. From this, we see that a very strong magnetic field would be produced if several of these atomic magnets could be aligned inside a material. This doesn't occur because our simple model is not the complete story. A thorough analysis of atomic structure shows that the magnetic field produced by one electron in an atom is often canceled by an oppositely revolving electron in the same atom. The net result is that the magnetic effect produced by the electrons orbiting the nucleus is either zero or very small for most materials. Okay. The magnetic properties of many materials can be explained by the fact that an electron not only circles in an orbit, but also spins on its axis like a top, with spin magnetic moment as shown in the figure. Note that this classical description should not be taken too literally. The property of electron spin can be understood only in the context of quantum mechanics, which we will talk about in another topic. The spinning electron represents a charge in motion that produces a magnetic field. The field due to the spinning is generally stronger than the field due to the orbital motion. In atoms containing many electrons, the electrons usually pair up with their spins opposite each other so that their fields cancel. That is why most substances are not magnetic. In certain strongly magnetic materials, for example, iron, cobalt, and nickel, the magnetic fields produced by the electron spins don't cancel completely. We call these ferromagnetic materials. In ferromagnetic materials, strong coupling occurs between neighboring atoms, forming large groups of atoms with spins that are aligned, called domains. The sizes of these groups typically range from about 10 to the minus 4 centimeters to 0.1 centimeters. In an unmagnetized substance, the domains are randomly oriented, as shown in the figure on the left. When an external field is applied, as in the middle and right figures, the magnetic field of each domain tends to come nearer to alignment with the external field, resulting in magnetization. In what we call hard magnetic materials, domains remain aligned even after the external field is removed. The result is a permanent magnet. In soft magnetic materials, such as iron, once the external field is removed, thermal agitation produces motion of the domains and the material quickly returns to an unmagnetized state. The alignment of domains explains why the strength of an electromagnet is increased dramatically by the insertion of an iron core into the magnet's center. The magnetic field produced by the current in the loops causes the domains to align, thus producing a large net external field. The use of iron as a core is also advantageous because it is a soft magnetic material that loses its magnetism almost instantaneously after the current in the coils is turned off. Now we can understand why ferromagnetic substances are attracted to permanent magnets. The magnetic field of a permanent magnet realigns domains in a ferromagnetic object so that the object becomes temporarily magnetized. The object's poles are then attracted to the corresponding opposite poles of the permanent magnet. The object can similarly attract other ferromagnetic objects as shown in the photo here. You can see that the other magnets are magnetized. I said magnets. Other magnetized paper clips are attracting others. Okay, we can classify materials according to how they react to the application of a magnetic field. In ferromagnetic materials, the atoms have permanent magnetic moments that align readily with an externally applied magnetic field. Examples of ferromagnetic materials are iron, cobalt, and nickel. Such substances can retain some of their magnetization even after the applied magnetic field is removed. Paramagnetic materials also have magnetic moments that tend to align with an externally applied magnetic field, but the response is extremely weak compared with the ferromagnetic materials. Examples of paramagnetic substances are aluminum, calcium, and platinum. A ferromagnetic material can become paramagnetic when warmed to a certain critical temperature, the Curie temperature, that depends on the material. In diamagnetic materials, an externally applied magnetic field induces a very weak magnetization that is opposite the applied field. Ordinarily, diamagnetism isn't observed because paramagnetic and ferromagnetic effects are far stronger. In the photo here, a very high magnetic field exerts a levitating force on the diamagnetic water molecules in a frog. Okay, this ends the section on magnetic domains and also ends the chapter discussion.